In this lesson module, we cover angle basics, including what is an angle, how do we measure it, and what are some of the basic theorems. But first, an angle is the measure of turn around a point. So if I have that point in green shown there, the turn from one ray to the next is the angle. How do we measure that angle? Well, the first way is radians. This is probably less common on the exam, but you should know it nonetheless. A radian is essentially the radius of a circle. Imagine it were a string, so you could lay it around the circumference of the circle, and the angle swept out from the central point, we would call that a central angle, is the same as the arc distance covered on the circumference by one radius. And we call that angle 1 radian. And as you might guess, there are 2 pi radii that go around one full circle. Degrees is the far more common measure you'll run into in practice on the exam. A full circle rotation in degrees is 360 degrees. So 90 degrees is a quarter circle, 180 degrees is a half circle, and 360 would be a full circle. So what types of angles will we typically confront, and how do we categorize them? An acute angle, shown on the left, is less than 90 degrees. A right angle equals 90 degrees, and that's denoted by the little square on the angle. An obtuse angle is greater than 90 degrees, but it's also less than 180 degrees. If it's exactly 90 degrees, it's a right angle. If it's exactly 180 degrees, we'd call that a straight angle. In between, it's an obtuse angle. And what if it's more than 180 degrees? Then we call that angle a reflex angle. Now, a couple typical relationships and words we'll use related to angles is complementary angles and supplementary angles. Complementary angles sum to 90 degrees. So angle A plus angle B shown sum to 90 degrees. You might also see supplementary angles. In the case of supplementary angles, angle A and angle B sum to 180 degrees. So now we've quickly seen what is an angle, how do we measure it, and some basic categories of angles. Let's start looking at the theorems. 3 typical angle theorems you'll run into on the exam are opposing vertical angles, angles along a line or supplementary angles, and alternate interior angles or transversals. So what exactly are these theorems? Well, we know opposing vertical angles occur when 2 straight lines intersect. The angle A and the angle B shown are opposing vertical angles. And opposing vertical angles are congruent, which really just means they're of equal measure. So angle A equals angle B. If angle A were 60 degrees, for example, we know angle B must be 60 degrees. Likewise, if we had angles C and D, they're also opposing vertical angles formed by the same 2 lines, and C must equal D in that case, because opposing vertical angles are congruent. Angles along a line, we saw just a second ago, they're essentially supplementary angles. They sum to 180 degrees. So we know the measure of angle A plus angle B shown must equal 180 measured in degrees. If I looked up at our first example, I know that angle A and angle C are angles along the line. So if A were 60, that means C must be 120 degrees, such that the sum of A and C is 180 degrees. Last but not least, alternate interior angles or transversals. Well, what do we mean by a transversal? Essentially, when M is parallel to line N, then any line that crosses over and intersects the both of them, in this case O, forms the following angles: Angle A and angle B are alternate interior angles. They're on alternate sides of the transversal, and they're both inside the two parallel lines. Angle C and angle D shown are also alternate interior angles. They're both interior to the parallel lines, and they're on alternate sides of the transversal. So, alternate interior angles are congruent, which again means they have the same measure. So angle A's measure equals angle B, and if we know angle A is 120 degrees, we know B must also be 120 degrees. And the same is true for angle C and D. Angle C's measure must equal angle D's measure as shown. And in this case, we also have angles along a line. So if B were 120, we know C must be 60 degrees. And based on our alternate interior angle theorems, we know D must also be 60 degrees. So these theorems will help us fill in missing angles and or set up equations to solve for angles in various problems. It's worth taking a second to look a little further at the transversals. Again, that is the scenario where we have parallel lines A and B, and they're intersected by another line shown, which we could call line X. Not only do we have alternate interior angles there and there, and alternate interior angles there and there that we just saw, there are also alternate exterior angles. So A and A are alternate exterior angles. They're outside the parallel lines, but on alternate sides of the transversal line. They are congruent. Alternate exterior angles are also congruent. B and B are also alternate exterior angles, and they too are congruent. Also, we may want to look at corresponding angles. This angle B is a corresponding angle to this angle B. They're both above the parallel line to the right of the transversal. So they are corresponding angles. Likewise, I could say this angle must be A, and that's a corresponding angle to this angle A, and they will in turn be congruent. So alternate exterior angles are congruent, corresponding angles are congruent, and alternate interior angles are congruent when we're dealing with transversals. The angle theorems we just discussed, opposing vertical angles, angles along a line, alternate interior angles or transversals, they go hand in hand on many problems on the exam with the sum of interior angles of a few common shapes. And we'll look at two of them in this lesson, the triangle and the quadrilateral. So for any triangle, the sum of interior angles, A, B, and C shown, where the vertex is not the center of a circle as we saw earlier in this lesson, but it's the vertex or corner of a polygon, in this case a triangle. So the sum of the angles A plus B plus C in a triangle must equal 180 degrees. And likewise, if I looked at a quadrilateral, which has 4 sides and 4 vertices, the angles inside each vertex, A, B, C, and D, they sum to 360 degrees. So let's put some numbers to that. Suppose this angle A shown were 30 degrees, and I know B was 60 degrees. Then in total that's 90 degrees, but they all must sum to 180 degrees, so I actually know C would therefore be 90 degrees or a right angle. And if we look at the quadrilateral, which again includes squares, rectangles, kites, rhombuses, parallelograms, etc., trapezoids, let's suppose that angle was 100 degrees for A, and B is 60 degrees, and D is 80 degrees, then I know that total is 240 degrees, which means my angle C should be 120 degrees. So even though it doesn't look like it's 120 degrees, diagrams are not always drawn to scale. Mathematically, in this case, it must be true that angle C is 120 degrees given the other angles shown, because they all must sum to 360 degrees. Let's put some of these angle theorems to work. Suppose I have the following diagram, where line segments AB and CD are straight line segments, and I have angles AB, C, D, and E shown. And let's further suppose we know B is 70 degrees, and angle D is 40 degrees. Can I derive all the other angles? Well, sure I can. I have a few different potential theorems at play here. I know A plus B plus C plus D plus E, all angle measures combined, encompass one full circle, so they must be 360 degrees. Likewise, I see some supplementary angles, like A plus B. They must equal 180 degrees. And in turn, I actually see opposing vertical angles, B and E, so I know angle B must be congruent with angle E, and we're given angle B is 70 degrees, so I know E is also 70 degrees. And A and B are supplementary, so that means A must be 110 degrees. 70 plus 110 form the angle along the line of 180 degrees. Lastly, I know E plus C plus D are also angles along the line, so they must equal 180 degrees in total. E plus C plus D. So D and E, in this case, are 70 and 40, and that will allow me to solve for C. C is 180 minus 70 minus 40, which is minus 110, and that turns out to be 70 degrees. So C is also 70 degrees. So we were able to derive all the angles, knowing supplementary angles, opposing vertical angles, and angles around an entire circle are 360 degrees. Suppose we had the following diagram. Let's try to fill out all the missing interior angles we can. I notice this is a quadrilateral. So I know this is 90 degrees given the square symbol. That's 90 degrees given the square symbol. Plus the 40 degrees and plus our missing angle here must sum to 360 degrees. So if I were to call that X, I know X plus 90 plus 90 plus 40 degrees equals 360 degrees, the sum of interior angles of a quadrilateral. So X in this case equals 360 minus 180, which is 180, minus 40 is 140 degrees. So X equals 140. What else can I fill out given that? Well, I know X and this angle here, we'll call it Y, are angles along a line. So Y plus X must equal 180 degrees. And if I know X is 140, Y must equal 180 minus 140, or 40 degrees. So Y equals 40. And I know if this is a straight line, that's 180 degrees, and these are angles along the line, which means this must also be a right angle. And now I have interior angles of the smaller triangle. I have 90 and 40. The sum of interior angles of a triangle must be 180 degrees. So A equals 180 minus 130, or 50 degrees. So 50 degrees is the value for A. How about this angle here? Well, that's an opposing vertical angle to Y. Two straight lines intersect, so that angle must be equivalent to my Y in 40 degrees. And likewise, these are two angles along the line, so one's 90, the other must be 90 as well. And that again means this angle here must be 180 minus 40 minus 90, or 50. So I've used the sum of interior angles of a quadrilateral, of a triangle, opposing vertical angles, and angles along a line, in this case, all four of those concepts, to fill out every missing angle within the diagram. Note the theorem relationships can be used to set up algebraic equations or problems to solve as well, as in this case. So if we have lines A and B parallel to each other, and we've got a transversal, line C, intersecting both of them, we want to know what is the value of Z. Well, right away, we know Z and y plus 20 are corresponding angles. So Z equals y plus 20. And we know Z and 3y minus 20 are angles along a line. So it must be true that they sum to 180 degrees. So that sets up an equation that Z plus 3y minus 20 equals 180. And since I know Z is really y plus 20, I can substitute y plus 20 for Z, plus 3y minus 20, the rest of the equation is the same. And now I've set up an algebraic equation and I can solve for y. So combine like terms. The 20 cancels with the 20. 3y plus y is 4y equals 180. Divide both sides by 4. And I will see that y equals 180 divided by 4, or 45 degrees. So, that doesn't answer the question quite yet. We solved for y, but the question wants to really know, what is z? Well, we know z equals y plus 20, so in that case, we can then simply say 45 is y plus 20 equals z, which is 65 degrees. So z is 65 degrees. That is the answer to the question. We use the geometry to create an algebra problem. And since we're having so much fun, why stop there? Let's look at one or two more. In this case, we want to know what is the value of A plus B plus C. And how would I look at that? Well, I know I've got straight lines, therefore I have opposing vertical angles, and that must be A. Opposing vertical angles are congruent. This interior angle of my triangle must be B. Opposing vertical angles again. And lastly, I could use the opposing vertical angles with C to determine my interior angle here must also be C. Now I know A plus B plus C are the interior angles of my triangle. Therefore, they must sum to 180 degrees. In this next problem, suppose we wanted to find the measure of angle A, shown here. How would I go about solving that? Well, right away, we're given 60, we're given 130, I see angle B. I know 130 and B are angles along a line, so B plus 130 equals 180. B must therefore, subtracting 130 from both sides, be 180 minus 130. B equals 50 degrees. So this angle measure is 50 degrees. How about over here, adjacent to the 60 degree angle? This must also be an angle along a line, so they must sum to 180. So this unknown angle, if we'll call it C in this case, C plus 60 equals 180. And C is going to be just 180 minus 60, or 120 degrees. So this angle is 120 degrees. Now I can solve for A. I know I have 3 interior angles of a triangle, 2 of which are given to me, 2 of which I've derived, actually, numerical values, so I can solve for A. A plus 120 plus 50 equals the sum of the interior angles of a triangle, which is 180 degrees. So A equals 180 minus 120 minus 50, which equals 10 degrees. So A equals 10 degrees, and the value of A here is 10. Last but not least, let's look at the following problem. If we're told length AB equals length BC, and we want to solve for Y, how would we go about that? We know we have an isosceles triangle because we have 2 sides that are equal. If the third side, AC, were equal, our interior angle would be 60 degrees for each of the interior angles of an equilateral triangle, but that's not the case here. We know one angle is 30 degrees. So actually, given that, if it's isosceles, these 2 angles must be the same measure. X and X, we'll call it. And we know from the sum of interior angles of a triangle, 30 plus X equals 180 degrees. So 2X equals 180 minus 30. Dividing by 2 on both sides, we'll get X equals 150 divided by 2, or 75 degrees. So we know our 2 angles here must be 75 degrees. And now we can go about solving for Y. 75 degrees plus Y plus 3Y are angles along the line, and therefore sum to 180. So 75 plus Y plus 3Y equals 180. Now we set up another equation in terms of Y, and we can solve for Y and answer our problem. So 75 plus 4Y, combining like terms, equals 180. Subtract 75 from both sides, and 4Y equals 105. Divide by 4 on both sides. Y equals 26 1/4.
Well,